Alright, hell yeah, we got material mechanics, and a person had a question that was like, hell, if you use Pythagorean's theorem to solve this, you don't have to use the angle final. And so we go into that in depth. This video is long as, but I'm doing it in reverse. So this is the concise version. Let's do it in 3 minutes. So the initial setup is like the length of the chord. So this side is going to be L over 2. The width down here is B, so just this is going to be B over 2. Cool, got it. And then you can find, oh, for the love. Okay, so anyway, let's get some more light. Hell yeah. Alright, so then you can use Pythagorean's theorem to figure out this one. Now, I made a huge error. I was just like, oh, this squared plus that squared equals this squared. Hell no. No. It's this squared minus that squared if you're going for a side. It was a huge hiccup in the normal video. You can spot that. I don't catch it till the very end. Okay, so that's the initial setup. Then the final setup is, hell, we're going to pull this some distance delta right there. So when we do that, we don't use Pythagorean's theorem on this one. We just say, hey, it's the original length plus delta. So that's what we did for this thing. And then we say, hey, the base doesn't change, B over 2. And then the chord was its original length plus some change in length. And so for this problem, we use that as, the person wanted to do it L over 2 plus x. But that means there's going to be an x here and then an x over there. So the total change in length is going to be 2x. So if we go to the spring equation, this whole thing is one spring with an original length of 0.76 and a K of 140 Newton meters. So the tension in the chord is going to be K, in this case, 2x, because it's just the way it's defined. Cool, so we have that. That's our first equation. Now, when we set up the free body diagram, I'm just going to choose a side. We know the forces are balanced, but I'm just going to say, hey, P divided by 2 is 40. They wanted 80 for the problem, but if you just take one of the tensions, we're saying 40 is equal to this vertical component. Like, obviously, you know, like the other tension will balance and it'll be 80. But we just want this vertical component. And then, so what I do is, you could do just T sine of this angle, and they wanted to use this angle original, you know, so that was, I think, in the question. They were like, hey, let's just use this angle as our initial and this angle as our final, and just use cosine, you know what I mean? But you don't even have to do that. Let's solve it using Pythagorean's theorem. So the cool thing about vectors, this comes from statics, is if you want to know the vertical term, you can just take the and let's say this is 40. Let's say this tension is 42. That was the example that I give. Well, we need to multiply 42 by a number smaller than 1, because 42 times like 0.9 might be 40. You know what I mean? Something like that. So so how to get that fraction is that you take any triangle that looks like this. It could be any similar triangle, and you say, hey, this length divided by the hypotenuse. Well, so it's this length divided by this hypotenuse is going to give you that ratio. So 42 times that ratio is going to give you 40. It's going to balance. So that's the force balance equation. So that's what we have right here. We have that tension. Could be 42. Could be whatever. That's going to be this side. So that's what we have in there divided by that side. So that's equation 2. This equation gets us hella close, because it's a function of that delta, what we want, but it's also a function of this change in length of the chord. We're calling that x, and the actual change in length is 2x. So we have this, and it has so this has t delta x. Well, this has t and x, so cool. We have 2 equations, but we still have 3 unknowns. We got t, x, and delta. So now we use Pythagorean's theorem just on this final setup, and we say this squared plus this squared equals that squared. Cool. It's just geometry. It has nothing to do with tension. It's just a play on geometry where you can get an equation with delta and x in it. So that's what we did right here. So we took this squared plus this squared equals the hypotenuse squared. And then we can take the square root of this. That gets it to L squared plus x, and then minus L squared over here. So we have an equation for x. Hell yeah. So now that we have an equation for x, we're good to go. This is our third equation. So you can throw this equation for x into here. throw t into here, this is going to be k2x, so then you have to throw that another x into there. So that's what we do. So we're going to, and then we bring the negative 40 over here, and we go to 0, and then we solve it in our calculator, and that's going to hella go slow, because I solved it 3 times, so it's going to go over the same point. But anyway, so we bring the 40 over here, so we got 0 is equal to negative 40, plus, and then t is equal to 2kx. So we got 2k. This beast is what x is. So it's just written all the way out. And then we're going to, like I said, we're going to multiply that tension. Could be 42. We got to multiply it by the ratio, some sort of fraction like 0.9. And that's going to be this top part. This vertical part divided by the hypotenuse. Well, the hypotenuse is L divided by 2 plus x. So then you throw that huge bear of a thing is x. I didn't throw another parentheses to designate x, because I didn't want to even throw another parentheses around here. Everything under this has to be divided by that. Now, you get close where you're like, hey, this is multiplied on top, this is divided by bottom. Man, you're so close to like just crossing this crap out, but you still have a L over 2. I'm terrible at simplifying things, so I couldn't see it simplified. It would be cool if you could just get one equation for delta, but there's some things in life that just aren't that way. You know what I mean? You can't just get an equation that says delta over here and then blah, blah, blah. And at the end of the day, it's just like, hey, you're just trying to find relationships. So now we have a relationship between delta is our output parameter, and then everything else is an input parameter. You know, you can set up the problem with a B, a K, a K, and an L. So hell yeah. So now I'm going to start the original video because my food is burning. And hell yeah, that was pretty good. 7 minutes in, and now you can just wade through, you know what I mean. No, it's not bad. I was just going to say junk and garbage and trash. But anyway, just do it. And, I mean, you know how we roll. You know how we roll. So, all right, let's start the video for real. All right, catch you on the flip side. All right, hell yeah. I guess one more thing, because part of the part of the question was like, hey, this person got 6.41 joules, and I don't know. I solve this in my calculator, and I get the exact answers in the back of the book. I guess I talk about that towards the end of the video. But anyway, because this person was commenting, I think they got to here, and then they used, you know, some sort of sign to get to relate that length. But anyway, so I guess I just got the exact answer in the back of the book, 100%. But I'd be curious about where they went, and then you know, I could look into that. But anyway, yeah. And then I copied this and whoa. But I did a nicer job. So here's the final equation that I have in my calculator. There, it's graphed and solved. What you do, basically I solve for this, it's 168.8 millimeters. That isn't the change in length in the chord, but then we go back and use the function of x and throw in that 100 or 0.1688 millimeters or meters, and then we can solve for the change in length. And obviously the change in length is 2x. But anyway, alright, let's start the video and you can watch the whole thing. Alright, sweet. Alright, hell yeah. So we got material mechanics, and I'm going to answer a question that was asked to me online. It was a question of why did I do an iterative process and potentially not getting the right answer. So that was the question, and so this person wants to solve it using Pythagorean's theorem, and it's a cool way to solve it because you just don't even have to find the angle. So we're going to draw this diagram in. This is the full length of the chord. So the total length is 0.76 meters. Now then we can draw a line right here. Now this distance across is b of 0.38. So we're going to say this is b divided by 2. And b is 0.38 meters. And so initially this angle initial is 60, and if you're pulling up with a load P of P is going to be 80 newtons, you know what I mean? Obviously this is a stretchy chord, and if you take what he was saying, if you take the equilibrium at this point, it's nonsense, because this chord's going to stretch because there's no force on the chord, you know what I mean? P right now is 0. And the second you load it up to 80 newtons, well, you're going to have that displacement, you know what I mean, whatever this displacement is. And that would be more reasonable. So why the iterative process, I'll just take about 2 seconds to say this. Why the iterative process worked when I did it to find the angle and it converged on it is because what we're trying to do is we're trying to find the tension in both of these. And so at 60 degrees, and again, if it looks like this, you know what I mean, and we're pulling up with 80, cool, 40 and 40, got it? But if this is hella out here, you know what I mean, it's like if you're climbing, rock climbing, this is death on an anchor. Because now if you're pulling up 80 newtons, like this is seeing maybe 800. So what we're saying there is the larger the angle, the more tension. So when we start out with an angle of 60 right here. And that's and it gets confusing because we're actually talking about this angle, you know what I mean? So let's just talk about this angle being 30 and 30. And so when we start out with a total angle here of 60, but then when we finish, this angle gets narrower. So if you recall what the hell I was just saying, the angle is steeper at the beginning, so hella tension. The angle slackens out after we put the 80 newtons, so not so much tension. And so why the iterative process worked is when you calculate the tension initially, you're going to get hella tension. And hella tension, now we go to the spring equation that says, hey, the force of a spring is K change in length. And this is the side, that hella tension side. This is tension. And so I can write it, tension is equal to K change in length. But we want to know the change in length. So now change in length is equal to hella tension divided by K. So we're going to get hella change in length, which is wrong. But then we go back, take that wrong answer, and throw it in. And now we're going to say, hey, initially this thing's way hella stretched. And now we're going to use that as the initial condition. And when we do that, it's going to say, whoa, there's hardly any tension. Tension's pretty close to just 40, even Steven. And then when we put that in, even Steven or less, then our change in length is undershot. So first we overshot hella, then we undershot, and then the iterative process will jump back and forth and then start to converge on the angle final, which was like 69.11 degrees. But regardless, the cool thing is we don't even need to solve for this angle. And it's kind of cool with trigonometry. You can do things so many different ways to get the answer. Now, I'm going to do everything that he does up to this point, and then once he... or I mean, I shouldn't say he, it's just a person. But anyway, once this person says, hey, let's use sine, you know, let's come up with the angle. Well, we're not even going to do that. We're just going to use all Pythagorean's theorem. Okay, and that's what this person wanted to do from the get-go anyway. So what we have is we're just going to take half, you know what I mean? Because if we know that the tension over here is going to be the same as over there, so I'm just going to simplify this and say this is 40 newtons. We're just going to solve half the puzzle. And the person, that's kind of how they lay it out. This is still b over 2. Now they say, and there was a little bit of an error, because I went through and basically got the answer in the back of the book. And this one, hey, I still got an energy of 0.641 joules. And this person is like, yeah, it's like, you get to a point where you're just like, no, I think I'm right on this. And it would be, I would like to see exactly from this step to this step how they're getting the solution. Because I think something interesting is going on. But basically the entire approach that we're going to do, that this person is doing, is just 100% awesome, and it's using Pythagorean's theorem. So let's do it. So now we're talking about the final, you know what I mean? Because that was the whole deal. If we're taking the free body diagram from when we put 40 newtons on, well, guess what? This already stretched. Now, the thing to not get confused about is the spring force is force of a spring, K, change in length. And this K has to involve the entire length. I don't even know where the hell that comes up. Oh, whoa, 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 whoa. It comes up in the fact that, hey, when we change the length, this thing goes from looking like this to maybe, hey, now it's going to look like this. And now here is the change in length. But if we want to do the diagram like this and this, we're going to have two little chunks of change in length divided by 2 and change in length divided by 2. So that's why right here, the person is like, hey, this is L over 2. Well, obviously, this is the full length. And so we're going to have length divided by 2. Cool. Plus. And then they just say plus x. And that's cool. I'll go with that. But we have to know that this x, at the end of the day, we need to go back to this and say, hey, this is the tension in the cord, and this is K, but our change is going to be now 2x. And this I don't think is where the hiccup came in, but it's just like, it's just spatial awareness. I would have probably set up the problem and said this is x divided by 2, and because then your tension is just K change in length, and we're saying change in length is just x. But we're going to go with it. We're going to say change in length. This x right here, but just know the whole change in length of the whole thing is 2x. Cool. All right, so now using Pythagorean's theorem, and again, let's go over it. So you have a, b, c. So we're going to say a squared plus b squared is equal to c squared. But now you got 3 terms. Anytime you have like an equation with 3 terms, you can totally rearrange it any way the hell you want to get the other terms. So we want this term. We want the b term. So we would go, hell yeah. B squared is equal to c squared minus a squared. And then we want to know what the hell b is. So we just got to square root both sides basically. C squared minus a squared. So that's what they do. So they say that this side, don't get confused, is L divided by 2 plus x squared. Now, am I doing this wrong? No, we're good. Minus b divided by 2 squared, and then the square root of that. So that's this right there. Oh, no. We need to get some bigger. We need to get some bigger paper, kind of start over, because they're also saying, hey, this is already friggin' stretched out, and they don't do it this way. I mean, obviously this is another equation, and this would be right. But that makes it harder. What they're gonna say is, hey, go to the original. This is just L over 2 before everything was stretched. And so then this, using that same thing, this is going to be, what is it going to be? This squared minus that squared. So this is going to be L divided by 2 squared minus B divided by 2 squared, and then square root of that. Now, because they went right for the problem. The problem says, hey, when you pull up on this, we need to move this a delta C. And the person just calls it delta. Cool. So we move it up a delta C. So then final is you're going to have this length. All right, hell yeah, we're on a roll. But final, you're going to have, the original length, that Pythagorean theorem, plus, so you're going to have that, I'm just going to bring it down here, plus that delta. So that original height plus the delta. See, this is the original height plus the delta. So that's the new Pythagorean theorem we're working out. I'm going to clean this up because I don't know why I'm just working with a tiny sheet of paper, but we'll do it. And so catch you on the flip side. All right, hell yeah. So now we're back, and we have this final term. We're going to have P up here. We're definitely going to have our tension down this chord, and now we have our Pythagorean theorem. And so now we actually have something to relate x to. We could say this squared plus this squared is equal to that. And now we have a function in terms of delta and x. But for engineering, that's just one equation, one unknown. So that's why you go to something like F equals ma. That's like a continuity thing. It's like, well, you do have this thing. We take a free body diagram, of, just of like this little piece of metal right there. And then we'll take a second to do that, because now we can chop that little piece of metal out of outer space, and we have a tension that way and a tension that way. And then we have a P going up of 80 newtons. So what Pythagorean's theorem says, this side is like, hey, we're going to do a scale and we're going to find forces. If we're force detectors, then if those forces are operating on a mass, so this is the side that's visible, then we should visibly see acceleration. So we're gonna identify that, hell yeah, we put an 80 Newton force. So now we ask the question, why don't we see acceleration? Isn't that what the hell this equation says? It says we've put a scale, we know that we have a force on a mass, but we don't see acceleration. You know, this thing's not traveling across time, you know, at a change in velocity, getting faster and faster and faster. It's not. It's just fixed in space. So, all right, let's just get to it. It just means that the sum of the forces in the y is equal to the sum of the forces. Yeah. But that's kind of a cool thing, is because now if we see a force up and we still observe acceleration at 0, a stationary object, then we know that there must be an equal force down. And this is how, if we don't see it spinning, you know what I mean, it must be balanced. You know, if we have a force up over there and a force down over here, well, we must have a force this way and a force that way. You know what I mean? So no net torques. In this one, we have all the points converging at a point. From a statics problem, torques aren't an issue, you know, because we're just taking, but the sum of the forces in the y equals the sum of the forces in the x, and obviously we're going to simplify it to just say 1t is equal to 40. So, and we do have an unbalanced thing here, but we know we're just taking half of it, and obviously this is balanced in the x direction. Cool. All right, so that's our setup, and that's our second equation. And one way to do a statics problem is you have like, hey, this distance right here divided by this distance is exactly what, like, you know, because like the problem diverges from, hey, if we knew this angle final, sine theta final is equal to this. And I'm just going to simplify. I'm just going to say this is A, and I'm going to do brackets like this plus delta. And we'll actually, this is all known quantities. L and B are known. We can just throw into our calculator. So this person's going to say, hey, sine theta final is equal to A plus delta. No. I so apologize. You know what I mean? Truly. Because... you know, it's cool to make mistakes. No, this is the hypotenuse. Where the hell am I going wrong? Oh, okay. So initially, I'm just putting these two triangles. I'm trying to bunch everything up. So if this was L divided by 2, and this was that, then this is L squared plus X, but we know that the full change in length of the chord is 2X. We've already explained that. This B2 doesn't change. But now what the hell is this? See, I'm just all out of sorts. It's, oh, no, we did it right, because, yeah, it just seems like it's, hey, it's this squared minus that squared. But we don't want that. We don't want another thing in terms of x. That was the whole point. So what we did is we just said, hey, no, it's just the original plus this delta. Okay, holy Toledo. So, yeah, I just got overwhelmed because, yes, whatever this, you know, you throw everything into here, this is a shorter number than that number. You throw everything into here, this number will be longer. Okay, so what sine says is that, hey, there's a ratio between this length and the hypotenuse, and that's important because in vectors, we're like, hey, what is this tension? Let's say it's 42 pounds. Well, of this 42 pounds, how much is in this direction? And it should be obvious, if this is 40 pounds up for one of them, this has to be 40 pounds. The vertical component is the only thing that can take this tension. That's kind of what that says. But this divided by this, the hypotenuse, so we'll go L over 2 plus X. Now this is a ratio. And if we go inverse sine, you know, we can find the angle. But yeah, this is a ratio, and it's somewhere between 0 and 1. So that's a good thing to know. But I'm not going to use sine. We're going to do something trickier. Because, so let's go back to our spring force equation. Force of a spring is K, change in length. So we know the tension in the spring is that spring force. Tension in the spring is K. Our change in length, though, again, it's 2x. You know, just to make sure. And so now, let's see. But yeah, so we got that. And so now our free body diagram says, hey, this P up has to equal this vertical component down. And so we would do t. So we're going to throw in t right here, and let's just, I don't want to write this 1,000 times. So we're going to go k to x. This is t. Cool. So that's t, but that's this tension. You know, that might be the 42 pounds, but we only have a vertical component, so we need to find that ratio. What you do is you just take this number divided by the hypotenuse. So that's what we can do. So we can say square root. And we can get hella easy now. So we're just going to go square root of a. We're just going to say, hey, that's this a term, delta, we can put some parentheses, divided by L divided by 2 plus x. Hell yeah. So now we have what relates, that load 40, you know, we're only doing half, but the tension in the cord is still the same. You know what I mean? The tension in the cord is the same everywhere. That's a function of tensioned ropes. Cool. So now that we have, but we still have 40 is equal to a variable of x and a variable of delta and a variable of x. So at the end of the day, what the hell do we want? We want to find delta. So we need to change these x's into deltas. And we can do that because we have this relationship. We can say that this squared plus this squared equals that squared. So let's do that. And so we're going to, this is just going to be a, because it's just all this. This is just a big old constant. Plus delta, but all that squared, plus b over 2 squared. And it's going to make my life easier. This is just I'm just going to call that b. So let's do that right now. Plus b squared is equal to L over 2 plus x squared. Well, and to save space, I do this all the time. Alright, hell yeah. To save space, I can just be like, well, let's just take the square root of this puppy, and now we have L over 2 plus x. We just want x, so let's go minus L over 2. It's a little bit sloppy, but hell yeah. Now we have an equation that's in x. So I'll write it again. X is equal to the square root, a plus delta squared plus b squared. A and b are just constants. And minus L over 2. Hell yeah. And so now, everywhere where we see this x, we can throw this in. And then this is just a function in terms of delta, and L is a constant. So now, I mean, these are massive equations, but I mean, so yeah, we'll do it. So what we're going to do, I mean, in my calculator, I said 0 is equal to, bring the 40 over there, negative 40, plus k 2x, and then we have to do the alpha a plus delta divided by L divided by 2, and then plus, well, now you got to throw this x term in, and we'll do it. So we got the square root of alpha a plus delta squared plus b squared, and you know what I mean. Now we don't have to write terms 1,000 times because these are just constants anyway. We can just throw them into our calculator as constants. Okay, minus L over 2. So that was all this x. We had L, you know, something plus x, and x is this minus that. Okay, cool. And that's it. So once we took our maybe 42-pound force, we're going to multiply it by this ratio, which is like 0.9, you know what I mean, because this just turns to 4, and we get 0. But it's whatever delta that does it. So we did it. We used equilibrium, and then we used the fact that the force in the spring, the tension is a function of its change in length. And we identified that change in length here is x, but we know it's 2x. So yeah, and then I just did it. And so I have it legit. There's the graph, you know what I mean, and we can trace it out. There's point. So the delta was 0.168, you know, 1818, and that's a delta of 168.2 millimeters. And just so we know we're on the same page, 2.712. 2.712. So we got 168.8. Whoa, 168.8. All right, so there is some discrepancy because I don't get that 168.8. Maybe I will run it the second time, but no, I get X is, let's see, 168.18. But that could be a typo in the back of the book. But I get the same energy. Yeah, it's just so interesting how yeah, books can have typos. But anyway, if you tackle a problem with like different approaches and you get the same answer, well then that gives you a better, you know, it makes you maybe feel. But I'm using the same techniques, so you know maybe there is something fundamentally I'm not doing. But anyway, so let's at least throw this into our calculator. So what we want to do is we want to, you know, alpha K is 140, you know, newtons per meter. So we got that. Alpha L is 0.76. Alpha B is 0.38. Cool. So we're all set there. So let's start putting these in. So we're gonna say B over 2, alpha B divided by 2. We're gonna store that. Well, that was dumb of me to store that as B as well. That's all right. So B is now B divided by 2. A is going to be this. So we're going to go alpha L divided by 2. Whoa. Squared. Alpha L divided by 2 squared plus alpha B divided by 2 squared. And then square root that. And that is what we're going to call alpha A. That's a constant. Okay, hell yeah. So now we're just ready to throw this into an equation and have it cross the x-axis, and where it does is where the delta gives us our value. Cool. Because we have two equations and we put them together. You know what I mean? So, yep. I want to make a video about that because I was just like, oh yeah, no duh. If you throw two equations and you put them together, well, it's where they cross is the answer. But then when you take all that junk and put it to one side, you know, yeah, if you have two equations and you put together because they have one similar variable, now you have now you have one equation on one side and one equation on the other with the same variable. So where those cross is the answer to your variable. But the second you get all that crap to one side, it's where that line crosses the x-axis at y is equal to 0. That's why this is the y term. You know what I mean? When y is equal to 0, you get your answer for x. But yeah, it's just fascinating that, I don't know. I just learned this as a, okay, we have a huge ass equation, one variable, throw everything to this side. Let's start typing. All right, negative 40 plus alpha k, 2, x is our, damn it. Okay, so again, we have another x here. So this right here, whew, it just gets ugly and big in our calculator. But we got to go square root of alpha a plus delta, all that squared plus alpha b squared, square root that, minus L over 2. Now, what a crazy headache. So if I just do K2 and then I start in on this, I need a parentheses there. I'm going to go square root. I need this parentheses, a plus delta. I need that parentheses plus b squared. I don't need any parentheses there. But once I get done with this, yeah, it's just fascinating. It's like I want to do this with minimal parentheses. I don't need any extra parentheses on L over 2 and squared. So let's go through this one. So when I get to here, I want this parentheses here. I don't need any parentheses on the L divided by 2. Plus the square root, same thing. A plus delta x. This is a plus x, so I need those parentheses. Don't need anything more, don't need anything more. All right, hell yeah. So all the parentheses, because these calculators, they just suck to navigate. You know what I mean? To actually go through this, you can take a look at it one time. It takes you a half hour just to get through your equation. Yeah, that's maddening. And so that's basically what we're going to type in, but we're going to have to type in less because we already saved these as A and B, so we did a lot of the legwork. All right, so negative 40 plus K2x. All right, let's start in. All right, and then square root alpha A. I'm already buggering it up. So we did the square root. We need a parentheses. Alpha A plus x is our variable. That's our delta, and it's just that one. That is so smart to actually just solve the equation for what the hell you want. Don't solve the equation for something else and then You know what I mean? But I do. I try to solve for the first thing I can solve for, store the hell out of it, and then work from there. All right. So squared plus alpha b squared. Done with the square root. So minus alpha L divided by 2. And then that's the final parentheses around that x value. Hell yeah. So, and this is crazy. You know, I'm going to lose my mind. I'm glad I caught my mistake. This x has nothing to do, so delete the hell out of that. K2, this x is that now. Okay, we want everything in terms of delta. So again, because I'm sure if you were looking at that, you're like, what the hell? We want everything in terms of delta. Now, when we throw it into our calculator, yeah, we can't type in a delta. You know, x is the only variable that will graph on a calculator. All right, so we're just saying, in this case right here, our wherever you see delta, in my calculator, it's going to be x. All right, moving on. So we got that, and now we're ready for this. So, yeah, I think we're good. I think we can just type in this, another parentheses, alpha a plus x, parentheses. And now we can just divide, but we do need a parentheses here. Alpha L divided by 2 plus the square root, parentheses, alpha a plus x, parentheses, squared, plus alpha b squared, done with the square root, minus alpha L divided by 2. And then this finishes off that parentheses, and we'll graph it. And it should, both lines, one should be blue, that'll be first, and then the red one should just perfectly overlap if we didn't make an error. And that's a hell of a thing for it to, like, okay, so you got the blue line, and then the red line should just overlap, for the love, please. And it's going to take the same amount. Oh, damn it, no way. Oh, did I not do the 40? Did I not do the negative 40? No, I did the negative 40. Bummer, man. Alright, so we need to go back and see what the hell we did wrong. Alright, so I'm going to do that on my own. Alright, hell yeah. So I found my error, and it was because originally this first equation had b in it. And b was supposed to be 0.38, but we totally changed b to b divided by 2. So then I went back and said alpha c is what we were calling this. So we're going to switch this to kind of alpha c. And then I got b back to normal. And then so for this second equation, everywhere where it says b, we got to throw in an alpha c. And I still think we have one more error, but maybe not. Maybe the graphs will overlap once we get all the alpha c. All the b's changed to alpha c. So I'm just going to double check, and I probably will have to pause because there's one more error. But that's the fun part about. I'm actually enjoying finding my errors, especially making videos. There's no reason to unless I'm thinking out loud and coming to a solution. No, that one was just painfully looking through what the hell, and there was no difference in the equations. I couldn't find a difference, but no, we still have a difference in the equations, and that's going to drive me up the wall. And so I still need to find out why these two equations are different. Now I laid them out differently. This one I multiplied by k2 at the end, or I mean this top one I multiplied by 2k at the end. And the x value at the end. This one I just went right into k2x, and but anyway, so let me just dive through both of these and see if there's just a small inconsistency. All right, catch you on the flip side. All right, hell yeah! So we're back, and I finally caught my error. I've been just staring at this for 15 minutes, but thank God I actually had the original answer. And for whatever reason, it actually is accurate to the back of the book. I don't know what the hell I was saying. We'll tackle that in a second. But what I did is remember when I switched b was 0.38, and then I said well, b divided by 2, and then that was stored as b. That was the dumbest thing I could have ever done. Anytime you choose a variable from the beginning, for the love of God, do not try to use that variable for anything else. That's the lesson that I learned, because when I stored this as a, see, my A is stored as that C value that I got. I turned, well, now I'm kind of confused. So what are we saying B is? B is, oh man. Well, now I actually don't know what the hell, for whatever reason, I typed this in. So anyway, let's figure it out. So I turned b back into normal. And so this term that I called alpha a was wrong. So now let's do it. So I'm just going to go the square root, and we're going to go alpha b, and b is back to normal. Is it? 0.38? You know, yeah, because it's way different. And then alpha L is 0.76. Yeah, so that's what we were storing as A. So we were just hella off and maybe doubly off. But anyway, that's here nor there. So, yeah, no, I get it. Yeah. We said this was B. You know what I mean? So then when I typed it in, I'm just like, well, that's B squared. And then I already turned B into point. So that's why it was reduced by a quarter. Yeah. Anyway, I think I see what my error is, but we can just move on. We found it. Now I'm going to store this. Whoops. Store this as alpha A. And hopefully all three graphs go through the same location. Because I retyped in the whole equation just to make sure I wasn't totally off. So there's the red line. We're going to have, blue line. We're going to have a red line and a black line. No, we're still way off. Bummer. Whoa. Yeah, those still are hella off. Well, might as well play around with this. So, again, square root alpha L divided by 2 squared. Is it plus? That's the other thing. It's just like, you know, is it plus? Because we're doing no. Okay. Yeah. So that's probably where our error is. I was just like, yeah, because we were saying this is this. It's this squared minus this squared. Even from the beginning, we went over the basics, and then I missed it. So you can do this is good. Like most of my videos are going to be good because no one's going to show their errors. They're just going to redo the video, and then you can do the video in like 5 minutes. Who cares? But yeah, so let's think through this. The hypotenuse is the bigger one. If we want to find this one, we got to take the hypotenuse minus this. Yeah, so we're going to do. And again, let's do it. So we have A, B, C. If we wanted to find A, it's going to be C squared minus B squared is A. And the square root of that is A. So that's what we have now. Whoa, damn. And so now this is negative. Wow, I'm sure you guys caught that from the beginning, but it's fascinating. That's why this is so good, because like, people are like, why would you post this if it's wrong from the beginning? But when you go to lecture, you know what I mean? And that is a weird term to use. I feel like I'm British. But anyway, you go to university, still British. But anyway, you go to college and you sit in a lecture. The best lectures are where the professor like barely has it, you know, with it. I failed the class, failed this material mechanics, from a professor that everything he said was 100% correct, and he said it once, and then he just moved on to the next thing, like that's all you needed to do. Like we were Johnny 5, and no, I was failing. And so I just had to drop the class, and you just question life at that point. But then I took it a year later, and I was able to get a different professor, maybe, because that other professor finally retired. Hell yeah. And this new professor, oh, he struggled. You know what I mean? And it was perfect, because we were like teaching him. We'd be like, oh no, you know, keep going. You know, like we're 2 steps ahead of you. That's where you're gonna learn the most, is when you have a professor that still is going to teach and know everything, but if they have a hard time grasping it, and you can grasp it too. I think we already explained it. All right, let's move on. And so there you go. And so now this is going to be. I'm just going to pull it up over here and then switch it to. Damn. So pull it up and switch that to a negative. Okay. So yeah, and we weren't too far off from our from turning this. I don't even want to go down that route. So now we're just good to go, and we're going to store that as alpha A, and that should do it. But I'm not 100% confident. Obviously, I was 100% confident like 2 minutes ago, and all the graphs were still all wrong. So blue graph, red graph should be on top of that. Hell yeah, hell yeah. Drop the mic. And then the black one. Okay, hell yeah. So now we got to go into the analysis of this problem because that was up for question. So we go for our 0 value. Well, I'm just going to go. So, and then what did I graph? So if I'm just trying to find the x solution, I'm going to go y is 1 to -1. So, y min is -1, y max is 1. And then my x, well, I know the displacement, this displacement, well, the back of the book says 0.168. Cool. So I'm just going to say it's between 1 and 0.2. So that's what I did, 1 and 0.2. And then, so I have a graph that's just going to throw a huge straight line at it. And if I want to go find it, go to the value 0.168, get close, and then go value 0, left bound it out, right bound it out. And then when it finds it, it's going to store it in your calculator. So you can go quit, and then you bring up the x value. And this is why you shouldn't store anything in your calculator as x, because once you go to an equation, it's going to solve for x, and it's going to change that value. If I go, I don't want to do it again, but if I go 2 stored as x, if I do that, it's going to, redo that. Well, let's do this. If I go 2 stored as x, it's going to do that. Go back to my graph. I'm going to go value 0, left bound, right bound, guess, and now I can go x is now that x value. So just kind of cool, and multiply by 1,000. So we do have this delta is 168.8. But now the second part of this problem wants to know about energy. And I'm not going to go over it 100%. I'm just going to say, well, we can. So energy is force times distance. And when you have a spring, it was back to that initial, and I won't bring up the literature again, but it's just like, yeah, this is the initial. There is P is equal to 0, or P is equal to 0, right at this initial condition, it's 0. And then P goes to a max of, well, we chose, half of the problem, but P goes to a max of 80. So now you have a force that starts at 0, goes to 80. What's the average force between 80 and 0? Well, it's the max divided by 2. So energy says, well, hey, you gotta take the average force if you're using the whole distance. Because if I use that whole distance, this thing stretches, that 2x. That's what we were saying. And it's 2x because of, the way that this equation was set up, or this part was set up. But yeah, it's going to take no force to stretch it that far. And then it's going to take half of max. No, it's going to take no force to stretch it, a little bit more to stretch it that, and a little bit more. You know what I mean? So there you go. So basically the calculus says, well, there's an average force average to stretch it this 2x. Cool. So that's the energy. Energy is the force average to stretch it the distance. And in this case, our distance is 2x. And x is not what the hell we just solved. This x is that delta. So that might be confusing. So now we have to go back to our equation and find an equation that relates delta and x. And so right here. So here it is. So let's just do this one, and we're going to go the square root parentheses alpha a plus x is now our delta squared plus alpha b. Holy hell. Yeah, we got into heaps of trouble. This is now C, and that's where we fell off a cliff by overlapping variables. That was so dumb of me. Alright, home stretch. See, now my confidence is just like 0 on the fact that this will come. It'll come out. L divided by 2. And so now we have an x of 0.1529. And this would be 152.9 millimeters. But that is this x. So the full change in length is 2x. You know what I mean? That's just because the person set it up this way in writing. And so I just wanted to keep with that. Just to see if that's kind of where the person got a wrong answer. But nah, I don't think it is. I think it... if I had to guess where this person got a wrong answer, they were saying something about using sine and cosine, and no, that wouldn't. If you used that, never mind. Sometimes if your angle's around like 44, sine of 44, you know, compared to sine of 46. Oh, I'm in radians. Thank God I didn't do anything with degrees. But yeah. Yeah, sine 44, sine 46. You know what I mean? Cosine 44, cosine 46. If you're off, you could be just off by just a little bit if you didn't use sine and cosine right. But now our angle's like 69. So sine of 70 compared to cosine of 20. Or I mean, those numbers are the same, but then cosine 70, sine 20. So obviously those numbers are hella different, so that's not where the small discrepancy. All right, let's get back to energy. So energy is force average times distance, and you know what I mean? Shoot. So the force is not. Oh, I apologize. Yeah, the force isn't this 80. They want to know the energy in the cord. So the energy in the cord is the tension force. That's the max tension, and we found that. That was K2x. So it's going to be, energy is going to be that tension divided by 2, and then times the change in length, and the change in length is 2x. So there you go. So that's going to be our equation. Tension. We have to use this. That's why these things double up, because we found the tension. Well, the tension was K2x. And then so you have to throw that in for tension. There we go. Divide by 2 and then multiply by the change in length. So that's why this is 1/2 K change in length squared. And the change in length is 2x. You know what I mean? So that's why definitionally, because springs are linear, you can just say the energy of a spring is 1/2 K change in length squared. You know what I mean? But you can also say, hey, energy is quote unquote force average times the distance, and the distance is that change in length, and the force average is tension, and it's spring tension because the force of a spring is K change in length. So yeah, so this tension force is going to be K change in length. So you're going to throw that in right there. Force average is K change in length, and D is change in length. So energy is and if this is the force K change in length, the max, well, the average force is K change in length divided by 2. So there you go. So this force average is K change in length divided by 2 times the distance you're traveling, change in length. That's where you get this 1/2 K change in length squared. Cool. I should make just a video on that. But anyway, we got to get to it. And so here's our equation. K, 2x, 2x, 2. And now we just solved for... What the hell? Did we even... I thought we plugged it in. Oh, I lost it, man. I apologize. All right, let's do it. So we got square root alpha A plus n... I'm going to swear. Okay, no. So our x is delta. That's going to confuse the hell out of me. All right, so we have square root alpha A plus x squared plus... Now, this b term, you know what I mean? Holy Toledo. It's just b divided by 2 squared. Man. Minus alpha L divided by 2. I shouldn't have done that one. That was dumb to do. Or it's just c. Well, let's see if I can get the same answer if I throw alpha c in there. Yeah, we're on the same page. Okay, so there you go. So this value is going to be x. I guess I'm just going to store it as theta. And now we got alpha k 2 theta 2 alpha theta. So k 2 theta divided by 2. All right, and so we get an energy of 6.546. So the back of the book should be 6.55 joules, you know, newtons meters. And this person got 6.14 joules. I don't mind doing it. I just, like this part of their question, I did not understand if they solve for sine theta and then use that to, like, you know, there's, for me, it's just like, I was like, that was sweet. Yeah, just use Pythagorean's theorem. You don't even have to use an angle. So that's what we did today. And I guess we're just going to look at the back of the book, 6.55. That should be the answer. And I'm going to call it. That's all I wanted to do. I thought it was going to be fast. Hell no. Doing math problems can be long and laborious. 6.55 joules. Alright, so I'm going to post this as an answer to this question. But I'm curious. It's like, where do you want me to? Do you want me to get to here and then, you know, use this second angle? I don't think that was necessary based on what. But yeah, I mean, I don't know. I mean, it's just at the end of the day, math sucks. No one wants to do it. That's why I just have a who cares attitude, and it's kind of fun to do. I hate puzzles. I like math because you just work with axioms. It's just like, no way. You can just throw in Pythagorean's theorem, even if it's just ugly looking stuff, and then throw them together and get a Hager's equation, but still it gives you an answer. I think that's magical. I love the axioms in math, but no, this was classic. We had a negative sign. Like, even my brother was just like, oh yeah, the worst things ever was just like, a positive needs to be a negative. Absolute insanity. But if you don't make mistakes, like, I'm just hella awesome at stuff because I'm going to make every mistake. I'm going to get fired from every job, but that means I'm going to have a lot of jobs, and I'm going to learn a lot of stuff. Alright, so thanks for joining me, and guess what? That's a video.